And I just turned on the recording. So,
Thanks a lot, Alicia.
yep,
Thank
it's all
you.
good.
Pretty fancy room. Our seminar room got designed by mathematicians.
Be careful, it's being recorded, so you want to say nice things about.
So they decided to put whiteboards on all the walls
Oh,
so that it's an echo chamber.
oh. But does that mean that the speaker can just kind of walk around the wall? This lecture as you go around?
Yeah.
Oh, really?
So put all the chairs and tables in a way that would make it awkward because it's tiny as well. Yeah, Maxine is out of town. So, But it's no excuse for not being on Zoom.
right.
Hi, Argotti.
Oh, I found his name. Okay, well, I think we can get started today. We're very happy today to have John Terning. John is a professor at UC Davis, and John has done extensive research in supersymmetric field theory, supersymmetry phenomenology, and beyond standard model in general. You can read his book on modern supersymmetry. He told me to say that. No, he didn't. No, he didn't. Definitely have a look at his book. Nice book. But anyway, today he's going to tell us. We're very happy to have him here, and today he's going to tell us about amplitudes for monopoles and the pairwise little group.
Okay, thanks for letting me come back. This is work that was done in various combinations with Chapa-Chapi, Semifon, Gary Sherman, Wigner, and Weinberg. Okay, so we'll start out with a review of monopoles, going back to Gauss. Then we'll figure out how to modify the S matrix. Weinberg's definition of the S matrix doesn't quite work if there's magnetic charges, so we'll fix that up. And we'll figure out the 3-point amplitudes using Onshell methods. And then we'll do Rubakov-Callan scattering, and we'll all be clear. So there are 3 problems with trying to understand monopole scattering. First problem is the Weinberg paradox. Weinberg showed that if you exchange a photon between an electric charge and a magnetic charge, you get a Lorentz violating amplitude. And there's poles in those amplitudes that are Lorentz violating. So that doesn't sound very promising. Another problem is that if you look at multi-particle states with both electric and magnetic charges, then they're not tensor products of the one particle asymptotic states, even if they're asymptotically far apart. So that's another challenge. And then the final problem is the Callan paradox. We're looking at scattering of gut monopoles. Callan concluded that the final states can include half particles that violate gauge charges, which also sounds pretty nasty. So we'll fix all those problems. So the first interesting paper about monopoles, it's not actually a paper, it's just in Gauss's notes. In 1833,
Three paradoxes. Don't they seem to be emerging from the flaws in the technical description of the monad? It's not a fundamental.
Yeah, there's
Kind
no
of
problem with
fundamentals.
monopoles. Monopoles are fine.
Well, in part because the product of the monopole coupling with the electric coupling, the electric coupling is very small, so the monopole coupling is very strong. And when you start trying to interpretation to it, it makes sense.
The way I got my head around that started with thinking about dark photons. Dark photons have dark monopoles. It turns out that dark monopoles can have epsilon coupling with dark photons. And then you can figure out what's going on in perturbation theory with that theory, and then that can come out.
In this sense, assume that the electron charge was not one free cell. Assume it was one free cell. You would have the same problem.
So Gauss announced in his notes that if you do this crazy integral, you get an integer, where these integrals are over two closed curves. And he just said this, and it was obvious to him. But you know, historians of mathematics go back and try to figure out what the heck, since this is the first topological number, and it's called the topological linking number, or Gauss's linking number. People reconstructed that what he was thinking about at the time was if you have a current going through a wire and you have a monopole, which is called a unit magnetic charge, going around some path, then that's what these two paths are referring to in his mind. And then just there's a relation between magnetic charge and the current. So what you can do, if you want to understand it in modern language, take, here's C is the path of the monopole. It's coupled to a magnetic field, so we can integrate the magnetic field around that curve. And we know the magnetic field is produced from this current. So you can use by Biot-Savart law to write down what the magnetic field must be. And you can also use Stokes' theorem to relate this first integral to the curl of magnetic field. He didn't have Stokes' theorem in 1833, so he did some complicated thing with geometry, but it gives the same answer. And then Maxwell's equation tells you you can write this in terms of the current flowing through the Stokes surface, and that's given by 4 pi times the current density. That I is the current, and m is the number of times the wire goes through the Stokes surface.
John, yeah, it reminds, kind of Chern-Simons, right?
Yeah, there's a related thing in Chern-Simons too.
Yeah.
It's also something you get in complex analysis because you go around groups twice the residue thing, right? And the integrated formula. It's the 4 pi n, that's what it's doing. It makes it like that. But there was no complex analysis.
Yeah, this is real analysis and topology.
Yeah, okay.
So comparing these, you can reproduce Gauss's formula for this linking number. It's just this horrible expression. Another way to think about it is the physics hand-waving proof. You could rewrite his integrand as a derivative acting on 1 over x. Then you could use the Stokes theorem, which brings in another derivative. And then you contract these epsilons, you'll get derivative squared acting on 1 over x, gives a delta function. The delta function is non-zero when the wire intersects the Stokes surface. Just counts how many times the wire goes through. So that's the easy way to do it. Okay, the next important paper about monopoles is Dirac's. Dirac was trying to figure out how monopoles work in quantum mechanics, and he said, well, I know how to write down the electromagnetic potential. It's got a singular line on it, but that singular line is just some gauge artifact. I can point it in any direction I want. So what gives? What gives is, he said, you can't detect it, and in the future, Aronov and Bohm will write a paper explaining that if you take an electric charge around a magnetic flux, you pick up a phase, and for this magic string, the phase has to be a multiple of 2 pi, so it's unobservable. And that gives you a relation between the electric charge E and the magnetic charge G. They have to be a half, the product is a half integer. And in that case, the string is unobservable. Okay. Next, Weinberg. Weinberg wrote this famous paper, Photons and Gravitons in Perturbation Theory. He derives Maxwell and Einstein equations from first principles. Kind of impressive. Everyone says that they've read this paper, but the final section, he talks about magnetic charges, monopoles. Nobody remembers ever reading that part. In that part, he says that, you know, the scattering is not Lorentz invariant, so that means that's why there's no magnetic monopoles, which was fine in 1965 because it was before Topological and Guts. So now we know there can be monopoles because we could just make them. Give me a non-abelian theory bigger than SE2 and I can make one for you, or bigger than E1 actually. So something fishy is going on. So the resolution of Weinberg's problem is that he considered one photon exchange, but as Misha was pointing out to us, the magnetic coupling from Dirac charge quantization is inversely proportional to the electric coupling. So the calculation of exchanging one photon makes no sense. You have to sum up all orders to get a gauge invariant set of diagrams. Fortunately,
No, yeah, John, I would disagree in the point that it's large, but when you go to large distances, where it's kind of Coulomb-like interaction, then magnetic charge doesn't matter, right? So at large distances, it's still applicable.
right. So the thing to do is go to large distances, or in other words, look at soft photons. Soft photons we can sum up to arbitrary orders because our expansion parameter is the soft momentum, we're not expanding in the coupling. So in another Weinberg paper, he explains how to do the soft resummation. And as you know, everything exponentiates. Now we have some extra diagrams in addition to exchanging, or in addition to emitting photons from the electric charge, we can emit them from the magnetic charge. We can also exchange soft photons between electric and magnetic. And when you carry that through, it again exponentiates, and you get an extra term. Remember, there's a Dirac string hidden in here somewhere. The Dirac string dependence is hidden just in this one phase piece, which I've called L. And with a little bit of massaging, you can write that in position space, and in position space, that phase piece looks like this. We consider the world lines of the monopole and the charge as closed by including the point in infinity, say, or if you wanted to measure this phase, you'd have to do an interference experiment, which would have some closed trajectory. So the monopole is on a closed trajectory, and we can use Stokes again on the electron world line and rewrite this exchange integral in this form, and it starts to look like Gauss. It's in fact a 4D linking number, and you get a delta function when you meet the Stokes surface of the electron meets the Dirac string. You get a delta function contribution. So that gives you a linking number between two world lines in 4D spacetime. And the nicest part is linking number is an integer. Q times G, Dirac told us, is an integer over 2. So this whole thing is I times an integer multiplying to pi. So it's an unobservable phase if we have direct charge quantization. So everything is Lorentz invariant, hunky-dory. We're happy.
But look, John, I still think that I agree about the phase. But if I write an amplitude as just one photon exchange between electric charge and magnetic charge, it's still applicable, you know, at large distances. It does not contradict what you say about phase, but I mean it would be the leading answer for the amplitude itself, right? Just Coulomb-like exchange. Your red box, I'm trying to say that it is one photon exchange at large distances.
Can you
But-
maybe repeat what Arkady said? Because
Uh,
it's not-
I, yeah, is there a way to turn up the volume or?
Not,
Not everyone can hear you. I'm having trouble hearing you too. But I think what you're saying is if you go if the electron and the monopole are far apart, then we should be able to calculate in perturbation theory just the one photon exchange.
right, and as I said, it's not in contradiction with your phase, right? But it would be the leading order.
That is true. And let's see what.
Because in this way you are going beyond this. I mean, you know, there is this kind of leading order, just Coulomb-like exchange, right? And then you can discuss this phase as you did, but in terms of kind of expansion, it would be next order in expansion. Because you are here, your red box, you can apply it not only at large distances. It could be kind of not a large distance. Then it makes sense to make it red. But if it's large distance, then it's not a red. It's just one photon exchange.
Well, I don't think I have a definitive answer, but my temporary answer is that if you look at what happens if you scatter an electron off a monopole and an anti-monopole, no matter how far away the anti-monopole is, then at leading order one photon exchange, you can get something that is consistent because it just depends on the dipole moment of the monopole anti-monopole pair.
No. Look, we have actually a paper with Adam Rees where we calculated for this Zyberg-Witten case in terms of this you know, perturbative exchanges, and it works very well near, you know, particularly it was near marginal stability curve. You see where effective interaction is small, right? You know, because there, I mean. Your effective Coulomb-like exchange, I mean, it's strong coupling in terms of strong interaction, but the effective Coulomb-like exchange, it is, I mean, marginal stability, the effective Coulomb coupling is small, so there is particularly useful. But I'm sorry, you know, we can discuss it later. Sorry, John.
Right. I'm looking forward to that.
What did Weinberg miss then? So why did Weinberg come to the conclusion that the Lorentz is not possible?
Well, the photon exchange propagator between electric and magnetic charges is what he showed.
No,
directly
but
as-
in Witten-Zyberg case, it was also exchanged by scalars as well, not only by photon. Yeah, because no, all mass is particle. I mean, involved.
Here's a Weinberg propagator. So just explicitly independent.
And how is that then fixed on the next page?
When you resum to all orders and for soft exchanges, that piece, that independence is exponentiated and only appears in the phase. And then the phase is a multiple of 2 pi.
May I ask a question? So what you refer to Weinberg, so he discussed basically the Dirac monopole. How would the advent of the standard of, let's say, George Glacial model, we can get a monopole in a better way, as you know, as solid on special type, and as you still broken down to the one or any transformation. So in this sense, we can, first of all, the monopole is the monopole for the extremes are equivalent. They are no longer single, right? They are physical objects. So is your formulation of the problem and your consideration applicable in this case when we know a lot more about it?
It's applicable in the low energy effective theory. So once we integrate out the heavy gauge bosons and hoops, we have an effective theory that just has the one. It's able to describe it both ways. Effective theory. Or
So you say that if monopole emerges, let's say in grand unification as a part of the model which appears identically in the model, basically no problems arises, but when you go to low energies and to effective description, monopole is a contract object, then there is a problem noted by.
Okay, so one more piece of history. J.J. Thompson also discussed monopoles. What he found is if you have an electric charge and a magnetic charge, there's an electromagnetic field between them, and you can just calculate how much angular momentum that field carries. It carries E times G times R hat. R hat is the unit vector pointing from the electric charge to the magnetic charge. So it's independent of how far apart particles are. It's proportional to E times G, which Dirac told us was quantized later. And you can also check that in the presence of a magnetic charge, your usual angular momentum doesn't satisfy the commutation relations. But if you add in this extra piece that Thompson told you about, then this object does satisfy the commutation relations in the monopole background. So you can, getting more general, we can think about particles that have both electric and magnetic charge, so dyons. So we have two particles, and the quantization condition gets generalized to E1G2 minus E2G1 as a half integer. And what this is showing us is that this quantization can be thought of as quantizing the angular momentum in the field. We have electric and magnetic charges, there's angular momentum in the field, and that has to be quantized as well. And that gives you the direct quantization condition. So that was the review. The review is over. So any questions, any more questions about review? Okay, so
maybe you could say, so you're trying to describe this low energy monopole.
well, eventually we're gonna get to scattering off a gut monopole, but it will be at low energies.
So now there's no formulation.
There's various wrong formulations that try to describe that. So to get to an S matrix, we need to think about asymptotic states and crucial into this little group. So what Wigner said is we pick for our particle, we pick some special reference frame with momentum k, and we can boost that with its transformation L sub p to an arbitrary momentum p. And then we can figure out all the representations by doing arbitrary Lorentz transformations on a state with momentum p. To do that, we break it up into some complicated set of sub-transformations. So we take k, momentum p, then we do our arbitrary Lorentz transformation lambda, and then we do an inverse transformation that takes the momentum lambda p back to k, and then we can do a transformation that takes k to lambda p. Which seems like it's all just doing and undoing things over and over again, but you can split it up into these two pieces. So this piece takes k back to k, but that doesn't mean it's trivial. It's the subgroup. These possible transformations are a subgroup of Lorentz transformations that leave k invariant. And that's the little group. So for a massive particle, we know that's SO3 or SU2, they are fermions. So we can label the particle states by their spin. And for massless particles, the little group is ISO2, which you can read about in Weinberg's book. But fortunately for us, the massless particles we know only have non-trivial quantum numbers under a U1 subgroup. So the photon has a helicity, doesn't have all these ISO2 quantum numbers. So we only worry about the U1 subgroup, and we label massless particles with helicities.
People try to make some mileage out of a continuous helicity or a few years, more than a few years ago. Right? But
Yeah.
that never came to anything,
Well, I mean, there's some math there, but there's no applications to the real world that I know of.
yeah.
But
People
you know,
try,
maybe
right?
someday we'll find some particles that transform under those.
Yeah.
But if they're massless, then you can't say that they're too heavy that we haven't seen them yet. So maybe they're
But-
very, very weakly interacting.
But still, I think the main point is that it is kind of that for massless particle is one-dimensional, right? Representation, right? So it is the main point, right? And it's so in this way it's just act like a charge, right? At the end of the day. So what could be changed here?
Well, the claim is that there are these infinite dimensional representations. That
Infinite
exist
dimension.
mathematically, but not in
Ah.
not for any particle we know about.
Yeah, no, but okay, infinite dimensional would be having infinite dimensional degeneracy, right?
Yeah. Okay, so now let's do little group when we have electric and magnetic charges. So we'll have, instead of writing E times G all the time, I'm going to call it Q. That's the angular momentum in the electromagnetic field. And what you can see is that if there's angular momentum stored in the field, and we do some Lorentz transformation, we're going to pick up a phase if we do a rotation, and that phase is going to be proportional to the angular momentum in the field, because that's what angular momentum does. This was first pointed out by Zwansger in 1972. He did a special calculation if Q is equal to 1, and he was able to calculate some amplitudes by putting in fake polarization vectors to represent this extra angular momentum.
If it's a diamond, do you have angular momentum? Just
If-
one single,
Single dion, no.
only when you
You
have.
need two,
separated,
yeah.
Because you need the direction from one to the other.
Yeah.
So here you have two dions, and then you have the angular momentum in the direction again between the two.
So this phase is what we're going to call the pairwise little group phase, once we have a pairwise little group. So just like Wigner, we need to go to a special frame where things are simple. And for two particles, the simple frame is the center of momentum frame. So they'll be back to back. Let's choose it on the z-axis. And now Pairwise little group is the subgroup that leaves both K1 and K2 are special momentum invariant. I think you can see that the thing that leaves an invariant is rotations around the z-axis. That means even if the particles are massive, this pairwise little group is just U1 for rotations around the z-axis. So in general, we'll pick up an extra phase. Through Lorentz transformation. And also, we've lost any notion of crossing symmetry now, because if we have two in particles that have this angular momentum between them, that's okay. And two out particles, that's okay. But if one is in and one is out, then you can't say that there's an angular momentum stored in the field.
But
So
why it's not,
crossing,
John? Why I would not say that it's no crossing symmetry. Maybe you can have more arguments in your arithmetics, because in this way you're right that it is changing this kind of relative stuff. But this is part of kinematical variable, right?
well, I mean, you can, if you say I had E plus E minus annihilates to monopole, anti-monopole, then in that case, there's no extra angular momentum in the field. But if I cross two of the legs, then there will be angular momentum in the field, both initially and finally.
No, but
So
this would mean that at some case, in one channel, this parameter equal to something, in the other channel equal to 0. So what is that? It's still not a breaking of crossing symmetry. It may be changing the rule of crossing symmetry.
okay, well, yeah, I guess you could redefine it that way.
Yeah.
So now, just like Wigner, we can figure out the induced representations. So we did it in a special frame with K1 and K2. There's a Lorentz transformation that takes us to an arbitrary frame with momentum P1 and P2. And then we do the same thing. We do a general Lorentz transformation on the state and the arbitrary momentum state in terms of the state in our special frame. And we can do the same trick of splitting it up into boosting to the general frame, doing our Lorentz transformation, then undoing it. And that will take us back to our special frame. And so this part of the transformation is the subgroup that leaves the special frame invariant again, which is the rotations around the z-axis. And that can only give us a phase again. So,
John, but may I ask you, in this way, this Q1, 2, which enters here, is it possible to write in terms of this Lorentz invariant, definition of your? No, normally, what was for say 2 amplitude? It was say S and T, right? I mean, two invariant. So I wonder whether number of invariants is changed or number of invariants is the same as it was for 2 particle. So it was kinematical, because Q1, 2, it is still kinematical, right?
Well, it just depends on charges. So on my next slide, I'm going to try to write the general state. So the general state is going to be labeled for n particles. There's n momenta, and then there's n spins or helicities. And then there's all the possible pairwise combinations of electromagnetic charges. And so under a general Lorentz transformation, the boosted state will pick up a little group factor for every particle, and also a pairwise phase for every pair of particles. And so we have to have these extra labels on our states that are pairwise helicities. Q1 up to Qn minus 1 n.
So essentially, it is in this way, this extra variables, right? This kind of this mark of pairwise helicities.
Right. So yeah, to label our asymptotic states, we need to include the pairwise helicities to specify things fully. Now we can work out an S matrix. We need some in and out states. So we do an extra in and out label plus minus. And then the Lorentz transformations, we'll have little group phases and pairwise little group phases, where we sum over all the pairs. But crucially, there's an extra plus minus sign in this phase. And one way to see that is go back to Zwanziger. You can calculate asymptotically what the angular momentum in the field is in terms of the asymptotic momenta. And again, there's this distinction between in and out with an extra plus minus. So that means when we write our S matrix element, we can boost to an arbitrary frame with an arbitrary Lorentz transformation. We'll pick up little group factors, but we'll also pick up pairwise little group factors. And pairwise little group factors don't cancel because of this relative sign. So if we have electric and magnetic charges in our scattering amplitude, every S matrix element has to transform with the pairwise little group phase. And that means we can't have forward scattering. So we can't have the usual thing that we expand around because it doesn't transform under pairwise little group. So now we want to use some Onshell methods to find out what the amplitudes are. So I'll remind you that we write everything in terms of spinors. So given a momentum P, we can use Pauli matrices to convert that to spinors. For massless particles, these states transform with an extra helicity little group phase. And for massive particles, there's an SU2 little group matrix. So that's ancient technology now, hopefully. So we need to extend the Onshell methods to pairwise. So we need pairwise spinors. So we need some pairwise spinors that transform covariantly under pairwise little group. They have to be associated with pairs of momenta. They must have a U1 phase, even if the momenta are massive. Normally, the massive ones pick up an SU2 factor. So what we need are no linear combinations for every momentum pair. We compose those into massless spinors. That's all we have to do. Fortunately, the null momenta were already introduced by Kossauer for doing some loop calculations. So if we go to the center of momentum frame, we have back-to-back momenta, and then just replace the energy by the energy it would have if it was massless. So it takes a massive momenta and turns it into a massless momentum. And then we can boost that to some arbitrary frame. So the flat is denoting that we've made this null momenta out of our actual momenta. And then in arbitrary frame, the actual particle momenta, so particle I and particle J, we can write those momenta in terms of these null momenta, plus and minus. So they're just linear combinations of each other. Yeah. It's actually very simple. I should have explained it simply. If I have a monopole here, an electron coming in, there's angular momentum pointing along this direction, say. If I went forward, the angular momentum flips. The angular momentum wouldn't be conserved in forward scattering. Well, it's just like helicity. The coefficient is quantized. You have some unit of helicity, and then there's a rotation part. Depends on how big your rotation is. So the phase isn't quantized, but the coefficient.
Yeah, John, it's okay to ask you at this point. Let me return back to this example I mentioned that, let's say we consider this Seiberg-Witten case, right? No, a supersymmetric one. Still, let's say that we are going to be near this marginal stability curve, okay? If we are sitting at marginal stability curve itself, then we have there, essentially non-interacting monopole and diane. Because effective interaction, this effective Coulomb-like alpha, which define interaction between, between dienes, right, goes to zero there. Okay, and moreover, if you go, inside of this marginal stability curve, this monopole and one monopole, particular plus minus magnetic charge 1, and one diene, this magnetic charge 1 and electric charge 1, becomes the only kind of fundamental particles, because everything is made out of them. And you have you see, so you have kind of near marginal stability, you still have kind of almost non-interacting particles, and they are fundamental, not original W boson or whatever, because those particles become composite made out of this. So in this way, it looks like they behave like a normal particle, right? And I wonder how your description applied to this particular case. The only difference is that there, besides massless photons, there is also massless scalars, exchange. And it's important because due to massless scalars, you have this compensation of, of Coulomb-like interaction. But you still can apply your formalism there, right?
I think so.
Yeah, no, with this additional massless scalars, right? So I wonder.
Massless scalar shouldn't carry any field angular momentum.
Yeah, right, but it's crucial because it diminishes interaction, because there is a cancellation. You see, on the marginal stability curve, there is this cancellation, and it kind of simplifies analysis in this way. So however, you still could see what's going on with your faces there in this limit, right?
Right.
Okay, sorry. Okay, again.
Oh, that's good. We're gonna do the Callan-Rubakov calculation at the end.
So,
It's not a asymptotic. No, the pairwise, that's what we're trying to construct with the asymptotic states were.
Yeah, of course, I would think of, I think that from that statement,
I mean, they are asymptotic states, but the way they scatter is not the usual way. I don't think that's required. Okay, so in our special frame, we can write down some spinners that correspond to our null special momenta. Then we can boost the momentum, so we can boost the spinners. And we can relate the spinners to some null momenta through Pauli matrices, same way we do in the ordinary case. And then these pairwise spinners under Lorentz transformations pick up exactly the correct pairwise little group phase, basically by construction. So now we can extend the Onshell amplitude story by constructing amplitudes out of the regular spinners for the particles, regular particles, and then using these extra spinners to account for the pairwise helicity. And these come with opposite weights, so we can do everything we need. What's going to be important for when we actually do real problems is the massless limit, because everything gets simple there. So in the massless limit, the plus flat guy goes to the particle spinner, And the minus flat guy goes to a parity flip spinner for the left-handed guys. And then again, the plus, the right-handed spinners go to the particle, and the minus goes to the parity flip. And if you can just check that in the massless limit, the plus right-handed spinner with the particle right-handed spinner and the left-handed particle with the plus flat spinner, those overlaps vanish. The non-zero overlaps particle with the minus and the flipped parity flipped with the plus. And that's going to be the main thing that drives all the surprising results at the end. It's going to require helicity flipping when we do scattering and special properties for lowest partial waves in Rubakov-Callan. So that's all the magic is right there. So here's the cheat sheet. If you want to build amplitudes, you build them out of either massless spinners or massive spinners and flat spinners, and they are associated with different little group factors. You assemble these to get the correct little group factors for your amplitude, and then you're done. So some examples: if you do spin half goes massive spin half goes to massive spin half and massless spin zero with angular momentum in the field of -1, then you can just write down what are the possible spinners that have the right properties. So we need massive spinners for our two particles. So that's the 1 and the 2. And then this guy is massless, I mean spinless, so we don't need any spinner for 3. But we do need something to make up the angular momentum in the field with Pairwise Little Group. So if we look at our table, we can make a Lorentz invariant by including the flat minus spinners, get an amplitude. So that's the only thing that gives the Lorentz invariant answer that is little group covariant. We do massive spin 0 to massive spin 0 and massless spin 1 with the Q of -1. Then it depends on the helicity of the photon. So the helicity of the photon is +1. Then we can easily find some combination of spinners. We have 2 3s because we need to get +1 helicity for the photon. And then 2 pluses for the flat spinners gives us the -1. But if we do helicity -1 photon, there's just nothing you can write. So this gives you a pairwise selection rule. Given the electric and magnetic charges, you can only emit 1 helicity of photon. So if we do incoming, now we know the rules, we can construct all the 3-point amplitudes. So the simplest one is an incoming massive particle and 2 outgoing massive particles. So depending on the spins, we need 2s spinners to make the total spin of each particle. So particle 1 has spin 1, then we need 2s1 spinners to make up this total spin representation. Do that for each of our massive particles. And then to make something Lorentz invariant, we contract it with these flat spinners. And notations, S hat is the sum of 3 massive spins. So then just write down all the things you can contract with these spinners to make the Lorentz invariant. And there are different, so we have some spinners, our flat spinners. They have some indices that we have to associate with particle 1, 2, or 3. So we have to sum over all the ways we can distribute the indices. But the powers are determined by the pairwise charge and the total spin. So
I was in, it's not only the pairwise, am I trying to is that on a multiple? Or I'm trying to do the pairwise, at least you work in just to make sure what
pairwise, you look at all possible pairs of particles calculate the product of electric and magnetic charges. If it's 0, then they're just like,
So
that's
each
it.
particle is still a spinner, right? So
Yeah.
I just have to take into account original.
Yeah, so here are the spinners that represent the 3 particles. We need to include all that standard stuff. And there's extra information we need to include to get the pairwise helicity transformation. So we build up these extra factors involving pairwise spinners, but these powers have to be positive. So that gives us a pairwise selection rule that the total spin has to be greater than or equal to the absolute value of the pairwise charge. An incoming massive particle, outgoing massive, and 1 massless. Let's do the unequal mass case first. So here are our massive spinners for arbitrary spins. And then we'll choose a basis. For the massless guy, we can choose the left-handed spinner and momentum 2 acting on the left-handed spinner, or we can on the right-handed spinner, and then we have our flat spinners as well. And then go to work finding all the combinations that represent the correct little group behavior. We get a whole bunch of terms. But again, the important point is that these powers have to be positive. And so constraining all of these to be simultaneously positive gives the selection rule that the helicity of the massless particle plus the pairwise charge in absolute value has to be less than or equal to the total spin.
So this is the basic amplitude then, and then you're going to generate all amplitude by recursion.
Yeah, that's ultimately what you want to do.
But these amplitudes, these are the first time that they were computed.
So for the example we did before with spinless particles, this selection rule tells you that the helicity has to be minus the pairwise charge. Pardon? Well, you can factorize on poles and try to build up higher things. You're talking about loop level.
No, I mean, so Massless case, you know, the BCSW is just lost, and then you can just go to any Pairwise amplitude. The Massless case, I'm wondering if there is a general.
Well, I'm going to only work at tree level for now.
No,
But yeah, I don't know the answer. If there's a massive recursion relation.
So like, you know, you have to invent some state, momentum state, right? That behaves in a good way in the UP. In this infinite circle in the investment. And I'm just wondering, in the Massless case, we know that concepts BCSW works, but in the Massless case, even without this monopole, I'm wondering whether there is any general momentum state that we can use without caring about this complexity.
Yeah, I don't know one. Okay, the hard one. We have an incoming massive particle and 2 outgoing massless ones. So again, it's a matter of finding everything that transforms the correct way under all the little group factors. So now there's lots and lots of terms. So sigma is the sum of the massless helicities and delta is the difference of the helicities. And requiring that all the exponents are positive again gives the selection rule that the difference of helicities minus the pairwise charge absolute value is less than or equal to the total spin or the initial spin. There's only one spin this time. So in all these cases, if you take Q equals 0, then you get Arcani Hamed et al. Selection rules. So that's just a cross check that we didn't do something crazy. Yeah. But as you can see that when Q is non-zero, you can get more restrictive selection rules like this. So it's consistent, but more restrictive than the usual case.
Right, just to make sure, so you're using this additional pairwise helicity as additional topological mass right? So what's the condition that I have to add this, like the narrow monopole?
Whenever in the initial or the final state, you have two particles that have a non-zero product of electromagnetic charges in the Dirac quantization sense. So if that Dirac quantization condition is non-zero for any pair of particles, then you have to include the pairwise helicity for that pair.
Just a non-zero link.
Well, I wouldn't call it linking number, but angular momentum in the field, or not mutually non-local is the way string theorists would like to say it. Whenever there's mutually non-local particles, then there's this extra phase.
Because you have defined a link, you have a variable linking number with the product of the charge.
That linking number was about the world line, so it was the product of charges times the linking number, so it's an independent.
John, let me again kind of try to refer to some particular case. No, just in example, as an example of your 3-point amplitude, right? Say in this scenario, which I try to describe near marginal stability curve, you can consider the following. You can consider W boson as consisting out of monopole and diane, okay? And it is 3-point amplitude, if you like, but all particles are massive and non-relativistic. So you see, so you have, say, kind of W boson decaying into monopole and diane. Okay, yeah, in your diagram, right?
Yeah.
The reason I'm asking, because in this case, kind of, everything is non-relativistic, but my impression is that it should be some simplification in your approach for this particular case. So I kind of call for you to check it out.
Yes, we were planning to check that out, but life intervened. But we'll get back to it, I promise.
Yeah, I'm sorry again, but anyway, but it looks like indeed kind of simple case, you see, because when you have almost non-interacting particles, right? I mean, with the weak interactions, it should be indeed kind of much simpler.
Yeah. Okay, so now we have all the 3-point amplitudes. We can do scattering. So what we can do is do the relativistic partial wave analysis. So using Pauli-Lubansky, we can find intermediate states with definite angular momentum. And then we can write our 2-to-2 scattering amplitudes in terms of a reduced matrix element that has all the dynamics hidden in it. And the angular dependence is in what's called the basis amplitude, which we can construct out of our 3-point amplitudes, because all the angular information is in there. So for example, if I had 2 incoming scalars, 1 and 2, and they went to a particle with spin j, and I can write down the 3-point amplitude, and then I can extract part of this Clebsch-Gordon factor that just has, that doesn't have, extract this spin j piece from the amplitude, and then combine that with the final state. I'll get the this to something else through the spin j intermediate state. So that's sort of the standard way helicity amplitudes were used back in the day, before they were cool. So let's do a fermion scatters off a scalar monopole. So we have some initial state and some final state. And we have our pairwise selection rules that, if we translate them, tell us that the angular momentum and the partial wave has to be greater than or equal to the pairwise charge minus a half. So there's a lowest partial wave where we saturate this bound. So the lowest partial wave is where the angular momentum is absolute value q minus a half. And a lot of work was focused on the case where Q equals a half, so that the lowest partial wave is scalar, but the same thing applies for for the lowest partial wave for any Q. So our incoming fermion will have helicity plus or minus a half. And we're going to work in the massless limit where everything gets simpler. So this will either be the ordinary massless spinner or the parity flip guy. So if we use people who do these things insist on using all outgoing conventions for momenta. So if we use that convention, then the helicity flipping case is where the helicity stays the same. If you follow it, because you're flipping the definition of momentum direction. So we can just write down what the angular part of the amplitude is. We have our fermion, final fermion spinners, and then we have to make up all the flat spinners so that we get the total little group covariance. And there's plus or minus up here. Whether it's plus or minus depends on the sign of the pairwise helicity. What you can see is in the massless limit, this factor out front will vanish for the plus case. So when the pairwise helicity is greater than 0, the amplitude has to vanish. If we do the opposite case where they're both, that was when they're both minus a half. We can do the case where they're both plus a half. You get this expression with the parity flip spinners. But again, in the massless limit, now with the minus flat spinner, this vanishes. So the amplitude vanishes when Q is negative. So in normal English, forgetting about outgoing, ingoing conventions, if the pairwise charge is less than 0, the only scattering that can happen is when a right-handed fermion flips to a left-handed fermion. And these are massless fermions. So they're not flipping because they have a mass, they're flipping from the interaction. And if the pairwise charge is positive, then the only scattering is if the left-handed fermion goes to the right-handed fermion. And putting things together, we can get our S matrix elements for positive and negative Q, has some weird angular dependence. And if you put in unitarity requirements, then the dynamical part is just 1. And then if we go back to Kazama, Yang, and Goldhaber, they had a 20-page paper where they solved the Dirac equation of an electron around a static monopole, and then solved for all the wave functions and extracted the scattering amplitudes and get this answer. Well, this calculation, takes 10 minutes. Worrying about all the details took a year. So.
No, but I mean, if you started with the rule.
Yeah, if you start with the rules, then it's 10-minute calculation. Okay, so finally, guts. Now, Q doesn't have to be conserved. Electric charge is conserved, magnetic charge is conserved, but I could have I can change my particles so that I have different number of particles in the final state. So there's different pairs that have different individual Qs compared to my initial state. No, so what matters is each pair. So I could have just to be extreme, we could have 2 photons in the initial state, and then E plus, E minus, and plus and minus. So Q is 0 in the initial state, but there's a pair here with a non-zero Q, there's a pair there with a non-zero Q, and then the same for this guy. So there's 4 different Qs in the final state, but in the initial state Q is 0. Okay, so oops. Here's our SU5 gut. I guess everyone has seen this. Has anyone not seen an SU5 gut? Okay, so what matters for us is that there's a broken SU2 called SU2 monopole, and the pieces of all this stuff that transform as doublets under this broken SU2 are these guys. And in our low energy approximation, we're interested in scattering off the monopole that comes from breaking this SU2. So think of this as an Polyakov piece. And so the interactions are between the monopole of this Polyakov SU2 piece and these four doublets. That's the simple way of analyzing it. So Rubakov-Callan, what they said was, we have two up quarks in the initial state. They scatter off the monopole. What happens? So the in state, we can write down that part of the amplitude. You just contract the spinner with the flat spinner, and that makes a Lorentz invariant combination. In their language, they would be saying that there's angular momentum in the field and angular momentum from the spin, and you line them up so you get a spin zero state, total spin zero state. You do that for each of the quarks. So what is the final state? You can't go forward, as we've seen. So if you went forward, you would have to have the plus flat spinner, but in the massless limit, this thing vanishes. So for massless, if we're in the massless quark limit, there's no forward scattering. And if you try to satisfy all the little group properties and the global SU4 symmetry, the only possibility is that you turn into anti-down quark and an anti-electron. And that's how they found baryon number violation. So if you added a third quark to this, it would be a proton, and then you would go to a lepton and a meson. So that checks out.
Related to the origin of the monopole and
Well, I mean, in Rubakov's analysis, he didn't worry about that. He was talking about there's an instanton, well, in the monopole background, there's this thing that behaves like an instanton, and it's at distances much larger than the gut scale. That's why the process is controlled by QCD, just PDF distributions, not by anything with gut physics. It's not suppressed by the gut scale. So this is long distance physics. So our low energy theory should reproduce their answer, and for the simple case, it does. So now we'll do Callan's problem. Callan said, what if I have a positron scattering off the same monopole? So again, the in state is easy. You line up things so you get a spin zero initial state or angular momentum zero state. But I mean, naively, you'd think if you have a positron going in and you violate baryon number, you could get a proton going out. But if you try to write down that proton final state, it vanishes again. So again, for the same reason that the flat plus spinner with the fermion vanishes in the massless limit. So you can't do the naive thing. Callan claimed, he had a long story about truncating to a 2D theory by throwing out higher partial waves and then bosonizing and this and that. And then he blamed Witten. He said, Witten told me that this is the only thing, because he wasn't so sure about it. Or I don't know. He said that Witten suggested this is the final state. But this half means that there are fractional fermions, whatever that means, because there are fractional, in the bosonized theory, there are fractional states, which makes sense in 2D, but I don't know what this means in 4D. And if you look at the gauge quantum numbers they're not conserved. And so then he suggested that you can interpret the half as half the time it goes to a positron and half the time it goes to a proton. And then on average, that will satisfy gauge charge conservation. Whatever, I think it's wrong. So let's do it a straightforward way. So we have his initial state, and we can write down a final state that is Lorentz invariant. These are things that would be dropped in his 2D truncation, so it wouldn't be surprising that he didn't find them. And so what we're doing is the down quark is being contracted with the flat spinner of one of the other quarks. And that other quark is being contracted with the flat spinner of the down quark. And then we have to antisymmetrize because of Fermi statistics. And so that's 1 and 2. So yeah, you can take the down with up 2 or with up 1. So the individual fermions in the final state are not in total j equals 0 states, but each factor has j equals 0. So you wouldn't see it in his truncation. He individually truncated each fermion to j equals 0, so you wouldn't see these things. So our claim is that this is the answer. You get a proton, not half particles. So
you're saying that the spin of the U2 is kind of paired with the spin of the monopole on B3.
well, this is the angular momentum in the field of D and the monopole.
Yeah. And that is kind of paired with this spin of the U3. So
Yeah.
this pair is and that kind of thing.
So summary, there's extra angular momentum in the field of pairs of particles with electric and magnetic charge. That means we need pairwise helicity and a pairwise little group to define the asymptotic states. That gives new selection rules in 3-point amplitudes, and all the surprises in monopole scattering are simply understood once you know about pairwise little groups. Thank you.
Very much for the nice seminar. Say anything about like pair producing monopoles and anti-monopoles?
I mean, you could. I think that's a process that depends on the physics in the core. So I don't think this will tell you the answer for that. You can say something about this other case I was talking about where you have a dark monopole that has an epsilon magnetic charge. And when you do the calculation there, it vanishes at 1 photon. So E plus E minus 2 photons of monopoles vanishes. So you have to go through 2 photons, and the dark photon coupling is epsilon. So that's epsilon to the 4th. So
How do you use that?
to get a perturbative calculation, right, I would have to do a non-perturbative calculation for a gut monopole, because it's not controlled by the low energy effective theory. But you can do this dark photon thing that you can do in the low energy effective theory, and it's perturbative. And then the leading process that you naively think would be there vanishes. So it's harder seems to be harder than you would think. That's all I can say.
Any other questions?
So when you can correctly, this construction to go from one particle state to two particle state to this interview solution of pairwise solution, but this is enough in the sense that to construct the entire particle space, you don't need any.
Right, for 3 particle states in 4 dimensions.
Yeah.
If you lived in higher dimensions, then you would have to do triplet-wise.
So in the sense, the Fox space is not the regular term of program. This is defined the first.
Okay, are there any questions online that anybody wants to ask?
No, I have a complaint, and it's not about John, because you know, in this Zoom version of listen to seminar, I can hear him very well, but I cannot hear really people who are asking questions, and I think it is kind of technically very simple stuff to arrange to having more microphone in the room, because you know, no, okay, maybe it is a way to scare people from using Zoom, but still I'd like to listen to others who are talking, you know. So I'm using John you to communicate this message.
Okay, Arcadia, we'll ask Alicia and try to figure that out. Otherwise, we
So-
can ask the speaker to repeat the questions next time.
So what
Yeah,
you're
yeah,
saying,
right. But, yeah.
you want your ITP seminars and your Santa Barbara sunshine too.
No, but in Santa Barbara, you know, they did in auditorium special arrangement to have you know, this microphone everywhere, and in this way there is no problem to listen to people.
Yes. We got them in Davis and then they kicked us out of that seminar room, so we never got to use them.
Mm-hmm.
All right, well, let's thanks a lot, Arcadia. We'll try to look into that, and let's thank John again for the seminar. Thank you.
I'm gonna try to figure out how to end the Zoom session.
Oh, yeah, someone will.
Some-
Okay, Jen, I can find you in
No,
about,
it's recording from mine.
yeah.